Hello, everyone. Welcome back to week 4. I hope that you had quite a nice break and a little bit of a change from this new routine. Now it's time to get back into the chemistry. So, guys, we're still building off of our last few weeks of work. However, this is the last week of Unit B. So we'll be tying it all up and starting fresh next week, week 5, with our next unit, organic chemistry. So keep that in the back of your heads. Alrighty, folks, here we go. Now, I'm going to keep saying last week. I recognize it was 2 weeks ago, but last week we were talking about voltaic cells. So essentially, types of batteries, basically, where spontaneous reaction produces electrons. So we end up with an energy output. This time, we're looking at the opposite. If we have a non-spontaneous reaction, how can we still force the reactants to turn into the products? And that's where we come into what's called electrolytic cells. And like I said, this will really be the all-encompassing focus of this whole week. So let's go into the design of these first of all. Now, let's just recall again, as I've said these different words, what exactly is a non-spontaneous reaction? Now, spontaneity is when we have that SOA, the strongest oxidizing agent, higher up on your table than your reducing agent. And by the table I'm referring to, of course, is this one, right? So, for example, if we have a situation where we've got silver ion and we have a tin 2 plus ion, this will be spontaneous. We're good to go. But what if we have a circumstance where the SOA is lower than the SRA? So, for example, what if we have a scenario something like this, where we're reacting H plus ions with, say, silver metal? All of a sudden, we're not going to see a spontaneous reaction here because the SOA is lower than the SRA. However, can we force this to happen? Let's get into it. Now, an electrolytic cell then uses an external source of energy, and specifically it's electrical energy. And the whole point of that is to make a non-spontaneous reaction occur, to force the reaction to happen. Now, sometimes these are their own unique reactions, but other times we can honestly just make a reverse reaction happen from an original spontaneous reaction in a voltaic cell. And that's the example I'll show you first. Let's think back to last week when we were looking at a zinc copper voltaic cell. And I don't think I actually told you the name of that cell last week. It has a special name. It's called a Daniell cell, and it's based upon who originally came up with it. And ultimately, it's copper and zinc. Again, we've looked at this example in great detail in your previous week's lesson, and we end up with no problem from a spontaneous perspective. So consider this. If you were to look at all the different items that are available, again, this is a familiar reaction from before, we would have the copper 2 plus as the SOA and the zinc solid as the SRA. So without a doubt, we have a spontaneous reaction because the SOA is above the SRA. Spontaneity, no problem. We still have electrons, of course, flowing from the anode to the cathode, and we're going to end up with that production of electrons, right? Leaving the anode, going to cathode. But what if we reversed the direction of the current? What if we forced the current to go the other way? Okay, let's consider our scenario then. Have a look at this table. They're not table, this diagram. Hopefully you guys are following along in your attached notes. We're now on the second diagram. Now, what if we want to do what's called recharging the cell? In other words, we're going to force, like I said, that current to go the other way. Take note, before the current was flowing from zinc to copper. Okay, that's still, as per usual, going anode to the cathode. Nothing changed that way. But what if we force the current to go from the copper to the zinc? Take note of something though. Previously, the anode was zinc and the cathode was copper. If we force the current to go the other direction, to head this way instead, notice that we end up changing the copper to the anode and the zinc to the cathode. In other words, the anode is still the one that undergoes oxidation and loses electrons. That rule doesn't change in any way, shape, or form. And yet, we have switched which electrode is the anode and switched which electrode is the cathode. We have forced, in other words, a situation where now that zinc ion is going to act as the SOA and the copper solid is going to act as the SRA. How did we force that change to happen? How did we force this non-spontaneous reaction to occur? Well, hopefully you've noticed in this diagram there's another distinct difference, and it's right here. In our previous voltaic cell, there was no battery. The electrons came from the spontaneous redox reaction. While in this case, we have to force the movement of those electrons. Hence, the application of a current with the battery. Ding, ding, ding. That's the key. A power supply is a part of an electrolytic cell. Okay, so check it out. Couple things in terms of comments about this. That power cell is pulling the electrons to go from the copper electrode, that's why it turns it into the anode, and then forcing them onto the zinc electrode. That's why the zinc is now the cathode. It's gaining the electrons because of this forced oxidation of the copper and forced reduction of the zinc. Now, if it forces the electrodes to essentially change what they are, then we're able to reverse the direction of the electrons. And we have, ding, 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 a new process, which is called electrolysis, and has made this into an electrolytic cell. So, let's keep on going here and talk about a comparison of these two. So what I would do if I was you is still have your pictures handy so that you can reference them as we're filling out this chart, because that's what we're comparing, right? The voltaic cell is your first diagram versus the electrolytic cell is the second diagram on the previous page. Take note, without exception, voltaic cells will always be spontaneous reactions every single time, whereas electrolytic cells are always going to be non-spontaneous. No exception. Notice too, we have opposites occurring here in terms of the transfer of of energy. Now, in voltaic, the chemical energy, right, from the redox reaction, the spontaneous reaction, is changing into electrical energy. Vice versa, with an electrolytic cell, we start with the power supply, the battery, and it's converting that electrical energy into the chemical energy. Again, these really are in so many ways opposites of each other. If you go back and consider what reaction is happening at the oxidation. Now, no exception, guys. Oxidation is always a loss of electrons, and it always happens at the anode. So for our voltaic, we have our zinc solid losing electrons as it becomes the zinc 2+ ion. So that's no change. And of course, a reduction reaction is going to have to be a gain of electrons. And in this case, it's the copper 2+ gaining 2 electrons and then turning into the copper solid. Remember, this is a spontaneous reaction. We put those two together, and no surprise there, we have a spontaneous redox reaction. And this is just like what we've been doing in previous weeks. Nice that the electrons balance out here, no problem, plus that copper solid. Done and done. If you continue to compare and we move into the standard cell potential, I filled in most of this already, but let's just go back. Think about that Chem 30 data booklet. And if we look at this again and do a comparison of our actual half reactions, then you'll see, where's my highlighter here, that our copper has a reduction potential of positive 0.34, right? Vice versa, if we move on to our zinc has a reduction potential of negative 0.76. All right, so go back in and we can plug these in to our actual ones. So copper was positive 0.34 volts, minus for zinc, negative 0.76 volts. And lo and behold, we end up with our positive 1.10 volts. Spontaneous, good to go. Okay, compare that to the forced electrolytic cell when we attached a power supply. In this scenario, we end up with our oxidation reaction. Still has to be a loss of electrons. That's what oxidation is. But now it's the copper that's going to be doing that. Hence, the copper is now the anode. Changes to copper 2 plus 2 electrons. Vice versa, we forced the cathode to be the zinc. So we're forcing the reduction reaction to be the zinc ions gaining 2 electrons to become the zinc solid metal. So in other words then, when we actually make that net cell reaction, notice something about this. Copper solid plus zinc 2 plus aqueous ions produces our copper 2 plus aqueous plus that zinc solid. Look at the two sides. We have an exact reversal. They are complete opposites to each other. And even if you go into the actual standard cell potential, look how this one goes. We have cathode and anode reversed. The zinc is now the cathode, so it's negative 0.76 volts minus the copper anode, positive 0.3 volts, 34 volts rather, which means suddenly the net cell potential is negative. Hint, hint. Spontaneous has a positive net cell potential. Non-spontaneous has a negative net cell potential. So have an awareness. The signs have reversed on these. Same absolute value of 1.10 volts, but reverse signs. Take note here that we have flips between our oxidation and reduction reactions and a flip between the reduction and oxidation reactions of voltaic versus electrolytic cells. That same flip switch opposite is seen for the net cell reactions. Knowing the distinctions and comparisons of voltaic cells versus electrolytic cells is a significant concept, guys. It's really important that you have that understanding between the two of them. Regardless, one of the similarities is no matter what, anode is where oxidation occurs. The anode always loses electrons. And vice versa, reduction is always where the cathode is, the reduction always occurs at the cathode. It's always where the gaining of electron happens. No exception. Okay, well, folks, just a couple other little things with this. A reminder to you about those negative values being specific for non-spontaneous, and just a little bit of background understanding here too, that minimum energy required is the absolute value of that net. So in other words, for the example that you were just seeing, you would have to put in 1.10 volts at minimum for us to be able to get that non-spontaneous electrolytic cell to actually function. Usually we end up doing an over voltage above that to really get it to go, but this is our minimum value. Okay, now there are some questions that you should start to do, guys. I don't want you to go into them until after I do the next part, podcast 2, which I'll do shortly here. I'll turn this one off. I really think it's important for you to look through this YouTube demo, watch the video before you actually attempt any of the questions. It'll make your life a little bit easier. So take a little break, get yourself a glass of water or something, and then come back and you can see podcast 2 before you start the assignment. Talk to you soon.